Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise and we'll be using the limit comparison test. Similar to the direct comparison test, we should have two infinite series to start with. One is the given infinite series and the second one is the one that we think which has the same behavior of the given test. Okay, so let's just read the statement of the test. So let's say like we have two sequences a and bn, and if you know that the limit of the ratio of an and bn is L, and if L is finite and positive, then the corresponding infinite series an and infinite series bn have exact same behavior. If one converges, the other one converges. If one diverges, the other one diverges. Again, Bn in general is not provided to you, so Bn is the one that you should come up with by looking at the overall view of the given infinite series. And if you can construct Bn for which you know the behavior exactly by applying the known tests, or if Bn is a very well-known type infinite series, then this test is very good and very effective to apply. Okay? So we're given two infinite series to work on, so why don't we get started?
All right, so let's start. We have the series 2 to the n plus 1 divided by 5 to the n plus 1. So this is going to be our an. Okay, so let's just write an here as 2 to the n plus 1. Plus 1 is not in the exponent, by the way. 5 to the n plus 1. Okay, so the limit comparison test says like we got to come up with Bn such that the series Bn should be a known series in terms of its convergence or divergency, so that I can sort of like compare an to Bn through this limit of the quotient an Bn. Okay, so staring at the very first example, 2 to the n plus 1, 5 to the n plus 1, if I did not have plus 1s at the top and the bottom, the series would look like a geometric series. Okay, let's see why. I'm going to say like this is Bn. Let's say Bn is the one having no ones. Okay, and as you see that this is 2 over 5 to the power of n. Okay, 2 over 5 to the power of n. So if I compare this series, let's say this is an, to 2 over 5 to the n where this is Bn, and I still have the same limits for the sum. So this is a perfect comparison. I wouldn't be able to use a direct comparison test because I wouldn't be able to majorize or minorize from the left to the right. That would be very hard. Okay, that wouldn't be possible in fact. Okay, so here the limit comparison test is sort of like better in a sense that you don't get to prove an inequality, but instead you are supposed to prove that this limit is going to be finite and positive if you want to prove for the convergence or divergence. Okay, so let's check what that limit is. Okay, so limit as n goes to infinity, 2 to the n plus 1, 5 to the n plus 1 divided by, let's say 2 to the n over 5 to the n. How about we leave it as this? Okay, and by the way, what do we know about the series 2 over 5 to the n? Well, we know a lot because it's a geometric series with the ratio to be like 2 over 5, which is less than 1. And geometric series are convergent whenever their ratio, the absolute value of their ratio, is less than 1, which is the case. I know, in fact, that this series is convergent. Okay? That's awesome. As long as this limit here is convergent and it converges to a finite number, we're safe to conclude that this series is also convergent because both series behave exactly the same. Again, if this limit is finite and convergent. So let me clean the right-hand side and then maybe we can just keep working on this limit. All right, so I'm going to just continue from here. Okay. all I'm going to do is I'm going to flip the bottom over. And pass the limit, obviously, but you're going to be careful because if I just pass the limit right away, 2 to the n plus 1 is going to converge to infinity, 5 to the n is going to converge to infinity, right? And 5 to the n plus 1 is converging to infinity. So it's infinity over infinity, okay? So we're going to be very careful. So all I'm going to do here is some algebra, as the way we did in Calc 1, okay? I'm going to pull out 2 to the n from the top, so it's going to be 1 over 2 to the n, and I'll do the same thing here, okay? 5 to the n pulled out, 1 plus 1 over 5 to the n, okay? And I still have 5 to the n, I still have 2 to the n here, okay? The good news here is that this 2 to the n is going to cancel this 2 to the n, this 5 to the n is going to cancel this one, so we're left with the limit of what? 1 plus 1 over 2 to the n, 1 plus 1 over 5 to the power 5. So now I can pass the limit. And the good news is that 1 over 2 to the n is going to be behaving like 1 over infinity, so this will converge to 0. This will as well converge to 0 because you're dividing 1 by a very large number. So eventually this limit value is going to be 1 plus 0 divided by 1 plus 0, which is 1. The awesome news is that this one guy here is less than infinity. So it's finite, in other words. Going back to the description of the limit comparison test, as long as this limit L is finite and positive, both series converge. So both series converge and diverge, I'm sorry. Okay, so going back to discussion here, okay, I have the limit, this is the limit value, right? This is the limit value, L, to be exactly equal to 1. 1 is less than infinity. So both series are convergent because I know that this geometric series is convergent. So it's important to find the second series with known properties so that you can deduce the same kind of like property for the given infinite series.